I'm Quincas and I'm a synth DIY guy. Welcome to my video on modular basics featuring the Erica Synths Das Kleine Fusion System. The Kleine Fusion is a slightly smaller version of the Fusion System 2. Basically the same, but without the Fusion Delay module, which reduces the size of the system to just 84 HP and saves you a bit of money. If you have your own outboard effects, like I have the Zen Delay right here, also by Erica Synths, you can get away with the system without any effects in it. It's a small but complete synthesizer with very unique sound due to the extensive use of vacuum tubes. Now this system is so complete and sounds so good that it seems many people are choosing it as their first modular, which is why Erica have asked me to make a comprehensive introduction to modular concepts using this system. I hope this video will be useful to everyone, whether you have the Kleine Fusion or not. So here we go, starting with the VCO. VCO stands for Voltage Controlled Oscillator. You'll see the VC prefix often because it means voltage controlled. So here we have a voltage controlled filter, a voltage controlled amplifier, and so on. The oscillator is a sound generator. It generates vibrations in a variety of different waveforms. You can think of it as a guitar string that's always vibrating. Some of those waveforms have dedicated outputs over here, and there's also a main output where you can combine a bunch of different features from the module. Let's start by just looking at and listening to the triangle wave. There it is, as you can see. It's perfectly geometric. It's a rising ramp followed by a falling ramp, and that's basically what a triangle wave is. Now the module gives me a few different ways to affect the frequency. One of them is with the octave switch right here. I'm in the middle position. If I push it up, you get an octave above. If I push it below the middle, you get an octave below. You also have a fine tune control here, which spans 2 octaves. It's mainly meant as a fine tune control so that you can play along with other instruments that may be tuned to A440, for example. Another way to control the frequency of this oscillator is by sending voltage to the 1 volt per octave input over here. I'm using an Arturia key step which has a pitch CV output. So if I plug that in here, now I have keyboard control over my oscillator, and it's perfectly in tune to the Western 12-tone equal temperament scale. Now, as I mentioned, this is a string that's always vibrating. It never ceases to vibrate. So that can be kind of annoying because you don't necessarily always want a note to be sounding. So before I continue looking at other features of the VCO, I'm going to introduce to you another concept, the VCA. We have 2 VCAs in this system. I'm going to use the simpler one, which is included with the Fusion Modulator module. And it's basically a audio input, an audio output, a control input, and a offset manual control right over here. Let me go ahead and plug that triangle wave into the VCA input right here. And we'll take the output right there. Now we don't hear anything because number 1, I'm not sending any voltage to the VCA CV. Number 2, the offset is centered. A VCA is a voltage controlled amplifier. That's the official name. I actually think of it more as a voltage controlled attenuator because mostly we don't use it to really boost signals. We use it to reduce volume so that we have silence. And here I would also like to stop and mention the 2 kinds of signals that we've already discussed. One of them being audio, which is an oscillation happening within the human hearing range of frequencies. So that would be between 20 Hertz, which is 20 cycles per second, and 20,000 Hertz or 20 kilohertz, which is 20,000 cycles per second. Really young people can hear that. Us older people probably only hear up to 17 or 18K or something like that. And the other kind of signal that we're talking about is the control signal. Control signals can be really any kind of voltage behavior, which is usually slower moving than an audio rate oscillation. So a low frequency oscillator is a good example of that, which is an oscillator that is also vibrating but at such a low frequency that you wouldn't be able to hear it as audio, but you can apply it as a control signal to affect a parameter in a different module. We'll get to that soon. And the VCA requires such a voltage in order to open up the volume of what we put in here. One way to apply voltage is to simply bring up the offset right here. So an offset is a way to add or subtract voltages. Towards the left here we'd be subtracting, but since there's no voltage going in, then we're subtracting from 0, and the VCA only responds to positive voltages, positive going voltages. So here's a way to manually open that VCA. We have the offset right here. We'll talk about other ways in a little bit. Right now let's go back to the VCO and have a look at some other waveforms. Another waveform that we have available right here, and I'm going to turn down our volume some because it's a much harsher sounding wave, much brighter, and that is the pulse wave. So as you can see here again on the oscilloscope, the pulse wave doesn't have ramps or curves. It's just alternating high and low voltages, and that gives you a much brighter sound. Here's the octave high, octave low. So compare that to the triangle, and you can see how they sound very different. The triangle has very few upper harmonics or overtones, and we can see that if I change my oscilloscope to a spectrum analyzer. We see that fundamental pitch right here, very strong. We see a little bit of a harmonic over here, and then nothing else. So it's a very pure tone, very mellow tone. And I can move that frequency with any of my ways to control frequency, right? Now when I change that to the pulse, suddenly we're seeing many more harmonics, right? I see 1, 2, 3, 4, 5 lines over there. Now the pulse wave has a peculiarity, which is the fact that it gives you control over the width of the pulse, and that can be done manually or via a control input. Let's do it manually for now. This is the pulse width knob right here. If I turn it towards the right, you can see how the upper pulse gets narrower while the bottom pulse gets wider. And you can hear how the timbre changes and becomes much more nasal, more mid-rangey, right? When I hit the middle and both pulses are equal, you hear that more hollow tone, which is the square wave. So here's another concept to remember. A square wave is simply a pulse wave with both pulses equal. Now if I start turning it counterclockwise, once again we get that nasally tone, right? I can even hear the exact moment right there when it becomes a square wave. It's a very different sound. Let's have a look at the spectrum analyzer and see what happens to those overtones or upper harmonics as we change the pulse width. See, you get more and more harmonics as you turn the pulse width. More and stronger upper harmonics as you make a pulse narrower. And here's a square wave again. Now another classic wave that most oscillators will give you is the saw wave. Now this oscillator doesn't have a separate output for the saw wave, so we're going to move on to the main output now, and I can assign which wave goes to the main output with this switch over here. The middle position is precisely the saw wave. And that's the sawtooth waveform right there. Octave higher, octave lower. You can also call it the ramp wave. And this also has way more upper harmonics than the triangle or a sine wave would have. Very cool shape. They get softer and softer as they go up, and there's more of them than on the square wave. Go back to oscilloscope. Now, one thing you may notice is that the ramp is slightly curved. The reason for that is we're taking this from the main out, which goes through the tube. So I'm not applying any tube crunch yet, but even so, it's going through it, and that changes the waveform a little bit. You can also see it with the triangle. That's the separate triangle output. If I turn the wave switch down to triangle here and take it from the output, you can see how it's a little bit curved, different than this one, right? And it even sounds a little bit different, which gives it a little bit of character. The same happens to the pulse wave. You see how it has that little ramp there rather than being perfectly square. Okay, let's go back to the main output here. Now, with the main output, we can start looking at some of the other features that this module offers. So one of them is the sub oscillator. It's a transistor and Vactrol based sub oscillator, which basically is an octave below the main pitch. And for that we have a color switch over here. It changes the way that sounds. It's basically a 3-step filter. So let's have a look. Well, we do have a sub output over here, so we can have a look at the effect of the color switch as we flip through the different options. So this is unfiltered, so it's a square wave. If I bring it to the middle, it's much darker sounding due to it not having that hard edge anymore on the rising part of the wave, and that's because some upper frequencies have been filtered. And then you have this one, which is even softer. It's filtered by quite a bit, so it looks like almost a triangle. And the volume control only affects the sub oscillator in the main output, so it's like a mixer, right? No sub, some sub. Here's the low sub, filtered sub that looks like a triangle with the triangle wave together. If I take it out, that's the triangle by itself, and that's the triangle with a sub. It's a fuller sound. These VCOs also have a detune function, which is a very interesting and unique feature I haven't seen in many oscillators before. And basically it's an analog bucket brigade delay line in there that adds a slightly detuned copy of the waveform. So you can hear this sort of less perfect, less in tune note. As you turn the detune knob up, not only do you get more volume for that second delay there, but it also speeds up the internal LFO, which is affecting the pitch of the detuned wave. So you can get kind of an extreme effect or something very subtle. Or even more subtle. And off. Another cool thing that this module does, and this is where the tube comes in, is the tube distortion or tube crunch, which is basically an overdrive. And let's turn down the VCA offset over here so we can see. And it turns it into a sort of pulse wave. Let's turn off the sub so we can see its effect on just the triangle. And clips the tips, making it look like a square wave. But it sounds a bit different from the normal square wave, as you can hear. Now we have two of these oscillators on either side of the filter. Why is that? Well, there are a lot more things that you can do with two oscillators than you can with just one. So let's have a look at those. Let's talk about another feature of the system, which is the mixer. The mixer is not its own dedicated module. It's part of the filter module. You have 1, 2, 3 inputs with their respective volume controls, and you have an output right here. The output is normaled to the input of the filter. Normalization is another concept that I want you to understand. Normalization is basically a connection that's already done for you from behind the panel. It's just handy and saves cables for things that you're probably going to use normally anyway. It's very common that you would mix the oscillators and maybe the white noise into the filter anyway. So Erica put the mixer in here and normaled the mix output to the voltage controlled filter input right here. However, normalizations can usually be interrupted simply by inserting a cable. The way to interrupt that would be to insert something into the filter input right here that would override the normalization from the mixer output to the filter input. And now we're going to send our oscillator into input number 2 here. And now I have an additional volume control, so I can even turn that offset all the way up here now and just use the mixer's level control. And now we're going to take the output of our first oscillator and plug it into input number 1 of the mixer. As we turn it up, we hear that second note come in. Now notice I have not sent the control voltage from the keyboard to this oscillator yet. So right here is one thing that you can do with 2 oscillators, is leave one as a drone. Right? If you're not controlling it with keyboard. Now, what if I do want it to respond to the keyboard as well? Well, that's where another handy feature that's included with the filter comes in. You have a multiple over here. You have mode in and 3 outputs. What the multiple does is it makes exact copies of a signal that you plug into the input into 3 outputs, making sure that no voltage or current is lost. If you were to passively split the volt per octave signal from the keyboard into 2 oscillators or more, you might start losing current, which will be heard as out of tune. So to send that control voltage to 2 oscillators, all I have to do is plug it into the multiple input and then take 2 outputs of the multiple, each to a different oscillator. And now I can use my tune to tune them in unison. Alright, so now they're in unison, and they're not perfectly in unison, so there you can see this sort of phasing effect, and you can hear it too. It sounds very different than a single oscillator. Let's hear it with a little bit of delay. Already we're getting into some very musical sounds here. Okay, delay off again before I have too much fun. And let's see some of the other things you can do. One of them is separate the oscillators by octaves. Right, so now this one is an octave above from this one, and if I turn the sub on, now I have 3 octaves happening. But also, you don't necessarily have to be in octaves, you can use a different interval. So this is in fifths right here. You can turn up the sub of the fifth as well. So we're starting to get more robust tones, aren't we? Here's major third. Now that's not all you can do combining 2 different oscillators. Another thing you can do is actually use them to modulate each other. And there are a few ways that you can do that. One of them is by using the sync function. So what sync does, the waveform will reset every time that it receives the rising portion of the wave from this one. So let's take the pulse output from oscillator 2 and plug it into the sync input of oscillator 1 here. the tune knob still works here, but it doesn't actually change the pitch anymore. What it's changing is the waveform. So why don't we have a look? Hear how that changes? You get different harmonics, different overtones. In fact, let's turn off this oscillator so we only hear the one that's being synced. And of course, in different positions, you will get different effects. So if you've ever seen a preset on a soft synth called sync, this is probably what's being done. Super nice. The other thing that you can do is frequency modulate one oscillator with the other. The word modulation simply means change, right? So when I say that I'm modulating something, it's a fancy way to say that I'm changing something. So I can modulate the frequency or the pitch of an oscillator manually like this, or with the keyboard. I can send it an LFO to create a vibrato. We'll see that a little bit later. But we can also send something that's audio rate, meaning it's vibrating at audible frequencies into the FM input over here, frequency modulation input. And then as I turn the FM attenuator up, and an attenuator is just the amplitude control, so when it's zero, nothing is going through. As I turn it up, I'm letting more and more of that incoming signal through there, and then I start getting some crazier sounds. And again, delay comes in handy here. When you're applying audio rate frequency modulation, you start getting into more bizarro territory. Let's choose the triangle wave for the output there, because since these are already pretty harsh sounds, it helps to use the less harsh wave. Once you find the sound that you like, you can actually play it in tune. This is another way to find different timbres. You can distort, you can change the waveform, you can use the sync, or you can use frequency modulation. And that's because this is a linear FM input. If you use an exponential FM input, you won't be able to play in tune. It'll be more for crazy noises and stuff. Let's hear what that sounds like. The 1 volt per octave input is an exponential input because we humans hear octaves exponentially, but the keyboard is generating a linear control voltage, right? 1 volt per octave. You're just adding volts as you go up each octave, but the frequencies need to be doubled. at each octave. So in the oscillator, as part of the circuit, there's something called the Exponential Converter, which is applied only to the 1 volt per octave input, or if we had an extra exponential modulation input. Get some pretty crazy sounds that way. Changing the waveforms too makes it different. Let's remove the subs for now. Get back to triangles. These are great for sound design and such. Let's go back to controlling both of them. If you think these sounds are reminiscent of more digital synthesizers like the DX7 or the Casio CZ, that's because they're frequency modulation or phase distortion synthesizers. Now, the one thing that I didn't mention about these oscillators is that they have an audio input, so we can actually add an extra sound source to go through the entire process here. Crunching, the detuning, the subgeneration. So to exemplify that, let's send that triangle wave into the audio input over here now. Cool. Now, so far, even though we are using a VCA, we've been controlling the amplitude manually, either with the VCA offset control or with the mixer volume controls right here. So I think it's time to introduce another concept, another type of signal, which is the gate signal. The gate signal falls into the logic category of signals, which also includes triggers and clocks. So a trigger is just a short pulse that starts an event. A clock is a short pulse that is rhythmic or repetitive or cyclical, and it's used to set sequences in motion and things like that. And a gate is simply an on-off kind of a signal. And my keyboard here has a gate output which reflects the key presses. So if I press a key, the gate goes high. If I release the key, the gate goes low. And what's that useful for? Well, if we put our VCA offset back in the middle here, so we don't hear anything, now it's waiting for a control voltage. And this modulator module here has two envelope generators. An envelope generator waits for an incoming gate and generates a rising ramp, stays up as long as the gate is high, and then when the gate goes low, you get a decay, also known as a release, depending on what kind of envelope generator you're using. Envelope generator output number 1 is normalized. Remember normalization? It's normalized to this VCA CV input right here. So I don't need to connect the cable from here to here to use this envelope generator to open up the VCA. So if I press manual, the envelope generator lights up. As long as I'm pressing the button, it's staying up, the voltage is still high, and it's opening up our VCA over here. Once I let go, it stops. The attack controls how hard or soft the note comes in. So it can come in gradually. Like if I put it all the way, it comes in gradually like that. If I put it in its fastest position, it'll just come right in. The same with the decay. If I have a slow decay, when I let go, it doesn't turn off right away. It takes some time. Gives it a tail. Now, this is a trapezoidal envelope generator. In the tradition of the EMS synthesizer, it has a looping function. So if you turn the off knob anywhere but maximum, you start getting a repetition. What it's doing is it's generating its own gate, and the gate length is determined by the on and off. So on is high, off is low, and the relationship between these two controls and the attack and decay controls determine the speed of your looping and also the voltage curve that it's generating, right? Start turning the decay slower. That repetition becomes slower as well. Same if I turn the off higher. If I turn the on higher, now we're getting a longer lasting high gate. But for now, since we're using a keyboard, why don't I turn the off all the way high, and now I will connect my keyboard's gate output into the gate input of this envelope generator. Now, pressing the key will be the same as pressing the manual right here. See? And now we finally have silence when a key is lifted. Now, if I have two keys pressed and lift just one, the gate's still high, right? So if you want to trigger the envelope every time, you have to lift your finger with every note. If you want the gate to just stay high, which is called legato, you just never lift all the fingers from the keys. And then it's just changing the pitch while the gate is high. Cool, right? Now, the modulator has a second envelope generator over here. And both of these envelope generators have two outputs each. One of them is the EG output, the envelope generator output, which is a positive only signal. It's a control signal that is positive only. So it's going from 0 volts up to whatever the higher voltage is. Now, the BP output means it's bipolar. What it does is it offsets it downward so that it's going from a negative voltage to a positive voltage going through 0, crossing through 0 volts. And that's useful for use as an LFO. So let's use our second envelope generator here as an LFO. And as we know, turning down the off will make it repeat. Let's have a look at that bipolar 2 output through the oscilloscope. I'm going to turn on channel 2 here, and we see that blue line going up and down. If we make it super fast, we'll be able to see the waveform a little bit better. There we go. Let's try to turn it into a triangle as best we can. So by combining the on and off with the rise and fall, I can achieve different kinds of waveforms. There we have it. That's kind of a triangular LFO happening here. Let's hear what effect that can have on different parameters that we have on our patch so far. Why don't we set both our oscillators to square waves and send the LFO to the pulse width modulation of one of them. Hear that? That's like turning this pulse width knob up and down really fast. All right, now we can make it slower, again, by changing parameters on our now LFO, not acting as an envelope generator anymore, because we are using the bipolar output and we have it in cycle. We can make it much slower, so it's a much more gradual, subtle change. And by changing the pulse width knob as well, we're offsetting that incoming voltage and getting different results as well. Another thing that we can do is apply that instead of pulse width, we can apply that to the FM. And now we can make it super fast and make it a vibrato instead. just make it subtle. Make it more extreme, and then it'll be more noisy, like a ray gun or some kind of alarm. Let's turn down oscillator 1 for now. Let's get some delay going there. So nice with that Zen Delay. Right? Follow me so far? Now let's get to the filter. This is a wonderful filter. It has 2 tubes in there, which are actually part of the filtering circuit, along with some Vactrols. So it's a very unique filter design. It sounds really wonderful. So what I'll do is, instead of taking the output from the mixer here to the VCA, we'll now take the output of the filter. And remember, our mixer output is normalized to the filter input. So I don't actually have to connect the mixer to the filter. That'll happen automatically. And now I can use my filter's cutoff knob right here to filter out high frequencies from my sound. Let's get that other oscillator in there. Let's turn off the vibrato for now. And that's that classic subtractive synthesis sound that we're all familiar with and love to death, right? A low-pass filter such as this basically has 2 controls. One is the cutoff frequency, so it's at which point the filter will start cutting the higher frequencies. And the other is the resonance, which is a feedback that generates emphasis on the very frequency that you're cutting it off. So if we have low resonance, you do get a nice sweep, but it's not super obvious what the frequency is from which you're cutting off the higher frequencies. Now if I start turning the resonance high, you start getting that peak. And it really emphasizes the harmonics of the incoming sound, right? Let's hear just one oscillator for now. Ooh, it's emphasizing that harmonic. Right? You can really hone in on those upper harmonics or overtones when you have the resonance high. Now, this is called a voltage controlled filter for a reason, of course. You have 2 CV inputs over here, control voltage inputs 1 and 2, and number 2 has its attenuator, built-in attenuator. So why don't we send that LFO that we were sending to the FM input of the oscillator, why don't we send that to the CV input number 2 here? Ah, listen to that. So now our cycling envelope generator, aka LFO, is a affecting the cutoff frequency of the filter. Let's hear that with some delay again. And of course the cutoff knob is an offset of that. Make it more subtle by turning the attenuator down. Have a filter on the delay as well, which is only affecting the repetitions. Resonance up there too. Listen to that. Beginning of a song right there. Let's turn off that CV level. So we're back to manual control only, because I want to show you a really cool feature of this filter that I've not seen on any other filter, which is the only digital component of this entire system, the CV record. There is a CV recorder over here that records for a few seconds the movement that you made on this potentiometer right here and sends it, it's normaled, to the CV input number 1. Of course, if I send something else, plug it into the CV number 1, it'll interrupt the normalization and you lose the record CV. It's still nice to have a second CV input. So let's try that recorder, shall we? You press the button and turn the knob, and it'll record your movements. So now when I press a key, turn this down so we really hear that. Those were the movements I just made, and they were recorded. And another interesting feature is that when that movement goes above a certain threshold, it generates a gate, which is this little LED you see light up over here, which you can use to trigger one of the modulators, envelope generators, or anything else. And now the knob itself, while it's not recording, it's playing, becomes a frequency multiplier for that recording. So if I turn it up, it's doing that same movement, but faster. Cool, right? That's with the resonance all the way high. Let's record a quick sequence here so that I don't have to be playing, and then we will play around with the filter a little bit. So record. I actually have my Erica Synths custom drum synthesizer here synchronized to the key step so that when we play around with the sequence, we'll also hear a beat coming out there. So let's record some notes here. That's good enough for now. Now let's record a new I want it to go faster. Very nice. Okay, let's record something a little more subtle. Nice, right? I really like this feature because LFOs can be repetitive, sample and hold can be too random, but this is just manual. It's just whatever you put in there, whatever you record. Why don't we turn on the delay too? I'll tap a tempo there. Now I can add that LFO too. Last repetition, filter the repeats a bit. Make it faster. Slower. All right, let's stop this again before I start having too much fun. Now, as you can see, already this is a very complete system only up to here. And we still haven't talked about this guy, the VCA Waveshaper Ring Modulator. And as the name implies, it does 3 different things. It also has 2 tubes in here, and they actually affect different stages of the VCA function that it has. But due to the tube nonlinearities, it also changes the shapes of the waves that we put in there. So why don't we have a look what that actually does? We're going to start by just listening to and looking at the main output here, which is a mix between outputs 1 and 2. Outputs 1 and 2 are tapping different parts of the circuit, so they'll have different sounds. Output 1 and 2 is a mix of both, and it's the only one that is affected by the drive here. So you have tube overdrive for this module. But we'll leave it down for now. Let's plug a triangle wave from right here into this input right here. And we can plug in another triangle from the other oscillator right there. So my input fader here, what it does is it fades between the two inputs. So I can change, for example, change the note of one of them, and as I crossfade them, you can get either of the 2 notes or a combination of both right there. Now let's choose just one. And here, let's turn off the delay for now. And here, what that does, what these bias controls do, they change the waveform. Now if I send CV, control voltage, so I'm going to take our LFO here, send it to the CV input number 1 here. Then by using the CV1 level, I can determine the effect that that incoming CV is having. Let's make it slower. So combination of the bias and CV input will give us different sounds. Now let's take, instead of the triangle wave here, why don't we take that VCF output? Let's turn that resonance down. Here's the drive. Gnarly, right? Drive down. And now, let's use the envelope generator that we've been using for the clean VCA here. Since we're now using this VCA, we can take the EG out 1 here and plug it in to our CV input. Now we can bias the VCA to be silent when we're not playing and leave the CV levels in their middle position. And now when I play, the envelope generator opens up the VCA. The CV level do some pretty funky things to how this VCA is responding to the incoming CV. See, when I let go, it actually goes louder right now. It gives me like a click, which is also very unique. I've never seen a VCA do that, and it changes the shape at the same time. It's all very kind of chaotic and strange and unpredictable. Let's get some delay in there again. Let's turn off the record here. Manually control the filter. Leave it static so we can really hear. And I can send the LFO now to our CV input 2. Generate kind of a tremolo. Very nice. Let's turn up the drive there. That faster. Cool. So that's its use as VCA/Waveshaper. Let's have a look at the ring modulator function. Plug them in directly. Triangle from one, triangle from the other. Ring modulator inputs 1 and 2. A ring modulator is a kind of bipolar amplitude modulation that you do in audio rate, also known as a 4-quadrant multiplier. So that's what we're doing here. We're using one to modulate the other. It's not entirely dissimilar from the effect you get from frequency modulation. You get these kind of bell tones. Which vary according to the relationship of frequencies between the two oscillators. And you can play them in tune. You don't lose the 1 volt per octave response. So now if I take from the main output here and plug our ring modulator output to the VCA input here, and our envelope generator back to the CV control here, we'll bring those biases back down. And I can drive that a little bit. So now I have keyboard control over this ring modulated sound, using the same module for both the ring modulation and the VCA function. Okay, we're getting there. Thank you for hanging in there with me. There are just a couple more things that I want to show from this very complete system. One of them is the white noise output, which I believe every system should have an analog white noise because it's just such a classic sound. So I'm going to plug it into the mixer here, third input of the mixer, turn only that up. We'll take the output to our clean VCA here, take the system output from there. We'll use the offset to turn it up. Let's turn off the delay for now. And this is white noise. White noise is a cascade of random voltages that happens at audio rate. It's like having all of the frequencies at once, which is why it's called white noise. It's an analog to the idea that white is all of the colors of the spectrum together, and you filter the color white to get different colors. Well, white noise is similar to that. It's great to do sort of ocean sounds or wind sounds. For wind with more resonance, you get more polar sounding winds, more whistly. So that's just super nice to have. And it is a nice white noise. Not all white noises are created equal. Lastly, I wanted to show you the sample and hold. So sample and hold, you have it on the modulator module over here. It has a voltage input, a voltage output, and a clock input. And what it does is at each clock pulse, it will see what the voltage is at the input and maintain that voltage steady at the output for as long as it takes to get another clock pulse. So it's a way to make something that's continuously variable step. So a white noise is a random voltage generator, as I've described just now, right? And that noise output is normalized again to the CV input of the sample and hold. So if I don't do anything, and it has its own built-in clock, which is the sample and hold rate over here. So if I don't do anything and just take the sample and hold output, and what we'll do is we'll take the pitch cable here from my keyboard and connect it to the sample and hold output. So the keyboard's no longer dictating the pitch of the oscillators, the sample and hold is. So let's turn up the volume of our oscillators over here. And what we're getting is a random sequence. And let's turn off any drive and any sub-octaves here for now. And this is the sample and hold level. It's just an attenuator. It determines how much how wide of a variation of voltage you'll be getting out of that sample and hold. So it can be, you keep the notes all very close together or make them jump. Very extreme kind of intervals. Now if I were to take, for example, the bipolar output of my envelope 2 and plug it into the CV in, now what we're getting is a stepped version of that rising and falling ramp. See? So what would be a continuous control is being sampled and held at this clock rate over here. And I do have an external clock input in case I want to synchronize this to my sequencer or to any other clock, to any other rhythmic element of my patch. Now we can also send that sample and hold to the FM inputs of the oscillators instead, right? So let's do that, and this will be the first time I would need to use an external splitter because I'm already using the multiple that's included for CV from the keyboard. And we will now, actually let's do it like this. We'll put this one back to the keyboard so we can vary the pitch now. And we'll take the sample and hold output into this little splitter over here and into both FM inputs. So let's make it random again. So I'll remove the LFO from the CV input. See, and now we can get a higher pitched random sequence there, more like R2D2. Let's turn on the delay for that. So with the keyboard I can determine how low or high I want that to go. And with the sample and hold level, I can go from steady note to slight variation to extreme variation. Turn up some detune, some sub, some crunch, and record a filter movement. Fun. This is what you might call a generative patch, somewhat. At least the pitching is generative. The clock is still steady. Now we could generate a random clock too. All we'd need to do is send that random voltage to another feature that I haven't mentioned yet. So these envelope generators have CV control over the decay. But let's do that with the left side function generator, because this one has an end of cycle output. And this is just a gate that goes high at the end of each cycle. So at the end of the decay stage of the envelope generator. And that'll vary because we're sending it a random voltage to its decay control. Now if I send that end of cycle output to the clock in of the sample and hold, we now get a random clock instead of a steady clock. There you go, this is a more generative patch. Very nice generative patch here. So I think I've covered everything. I've been recording for 1 hour and 40 minutes and this is going to be a crazy editing job, but I'm pretty happy. Let me just look at the system and see if there's anything I have not covered. This has gone so long that I don't want to take any more of your time, but I will mention a few things. One is that the Decay CV is very handy for percussive things as well. You can make a hi-hat, for example, by using a white noise to the VCA controlled by the envelope generator, and randomize the decay length will give you hi-hats of varying lengths, which will sound very musical and much less repetitive, almost like a drummer actually opening and closing the hi-hat. That's another use for the Decay CV. And the other thing I was going to mention is the fact that you have 2 VCOs and 2 VCAs, as well as a Waveshaper and a filter, allows you to patch the system duophonically. You can actually have 2 voices, right? You can have one VCO through this Waveshaper VCA, controlled by one of the envelope generators, be one voice, maybe controlled by a sequencer, and then use a keyboard to control your other VCO with another envelope generator through this filter, through the VCA that's built in here, and have a second voice. And you can even send them separately instead of mixing them in the system. Send them separately to your DAW or to separate effects processors or whatnot. So this system can actually be a 2-voice system rather than just a single, more complex voice. You can make 2 simpler ones as well. I won't do this on this video because it's been very long already. I think I'll stop for now. The main concepts that I wanted you to get out of this are the 3 main kinds of signals, which are audio, control, and logic, right? Audio being what's generated by a VCO and then affected by a filter or a ring modulator, a VCA, effects processors, etc. Control signals are the signals that you're not using to hear directly. You're using them to control parameters of other modules, and that includes envelope generators, sample and hold, LFOs, sequencers, keyboards, etc. And logic signals are just binary, meaning they only have 2 states, up and down, on, off, yin, yang. And they are the triggers, gates, and clocks, and they're used for rhythmic things or for setting things to motion and so on. I wanted you to understand the concept of normalization, where some connections are pre-made for you from behind the panel, but they can be interrupted with the insertion of cable. I wanted you to understand the concepts of exponential versus linear frequency modulation, what a filter does. Filter and VCA together are really what define this as a subtractive synthesizer, because you start like Michelangelo's David with a big block of marble and remove the excess marble until you find your David inside, and that's how you find your timbres on a subtractive system. You have an oscillator that's sounding all the time with a harsh sounding wave with lots of harmonics. Use your filter to reduce those harmonics and dial in the timbre you want, and the VCA to create silences. So it's a subtractive process from something that's always making sound with lots of harmonics to something that sounds when you want it to with the harmonics that you want only. So that's it for today. If you've made it this far, congratulations. Thank you very much for sticking with me. Please consider giving this video a like, subscribe to my channel, and maybe even pitch in on my Patreon. See you soon. Stay noisy.